In the grand architecture of the cosmos, two theories reign supreme: Einstein's general relativity, the elegant description of space, time, and gravity, and quantum mechanics, the restless mathematics of the subatomic world. Each works flawlessly in its own domain, yet when we try to merge them, the universe resists. At the intersection of these pillars lies one of the greatest unsolved puzzles in modern physics: quantum gravity. A theory that dares to describe gravity not as the smooth curvature of spacetime, but as something granular, quantized, and woven from the same quantum fabric that shapes all matter and energy. Before we get too deep into this topic, be sure to like this video and subscribe to the channel. This helps to bring more valuable content to the platform for your knowledge and understanding. Remember, knowledge is power. Now back to the episode. Einstein's general relativity treats spacetime as a continuum, bending smoothly around stars, black holes, and galaxies. Quantum field theory, however, describes reality as a set of discrete quanta, particles interacting through force carriers. The trouble begins when we apply quantum rules to gravity itself. If gravity has a quantum field, its hypothetical particle, the graviton, should mediate interactions between masses. But when we attempt to calculate how these gravitons behave, the equations diverge to infinity. Unlike the electromagnetic or nuclear forces, gravity refuses to be renormalized. The very mathematics that make quantum electrodynamics so precise break apart under the weight of the cosmos. Physicists realized to unite the large and the small, spacetime itself must become quantized. At around 10 to the minus 35 meters, known as the Planck length, the smoothness of spacetime is expected to dissolve. Quantum fluctuations become so intense that the geometry of space and time begins to foam and flicker. A storm of microscopic wormholes and curvatures called quantum foam. At this scale, both relativity and quantum mechanics fail to provide reliable predictions. Only a true theory of quantum gravity can describe what happens when the universe itself becomes a quantum object. This is where physicists diverge, proposing radically different frameworks for how spacetime might emerge from quantum principles. The first major contender was string theory. Born in the 1970s and refined through the 1990s, string theory proposes that fundamental particles aren't point-like, but tiny vibrating strings. Each vibrational mode corresponds to a different particle: photon, electron, quark, and remarkably, one mode naturally behaves like a graviton. Thus, gravity emerges not as a separate force, but as an intrinsic vibration of the string. String theory elegantly unifies all forces under one mathematical umbrella, requiring extra dimensions, usually 10 or 11, curled into compact manifolds known as Calabi-Yau spaces. In its modern form, M-theory, it includes membranes, or branes, and suggests that our entire universe may be a three-dimensional brain floating in a higher dimensional bulk. But there's a challenge. String theory's predictions occur at energies far beyond what current experiments can test. Its mathematics are breathtaking, but its empirical silence leaves physicists divided. Across the theoretical landscape, another school took a different path: loop quantum gravity, or LQG. Instead of adding new dimensions, LQG begins with Einstein's own equations and quantizes spacetime directly. It envisions the geometry of the universe as a web of finite loops, discrete units of area and volume called spin networks. In this model, space itself is granular. The smooth continuum we perceive is an emergent illusion, much like how a digital image appears continuous from afar. Pioneered by Carlo Rovelli, Lee Smolin, and Abhay Ashtekar, LQG removes infinities without extra dimensions or supersymmetry. It predicts that the Big Bang was not a singular beginning, but a big bounce, where a prior universe collapsed and rebounded. Unlike string theory, it's less about unification of forces, and more about revealing the quantum nature of geometry itself. Beyond string theory and loop quantum gravity lie several alternative frameworks. Causal Dynamical Triangulations, CDT, led by Renat Lal and Jan Ambjörn, builds spacetime from simple building blocks, four-dimensional triangles, or simplices. By assembling billions of these in a way that respects causality, CDT allows the geometry of the universe to emerge statistically. Remarkably, simulations have reproduced a universe that resembles our own at large scales. Another line of attack, asymptotic safety, proposed by Steven Weinberg, posits that gravity becomes self-consistent at extremely high energies due to a non-trivial fixed point. This approach preserves the continuum of spacetime but makes quantum gravity mathematically safe from divergences. In the late 1990s, a profound insight reshaped the field: the holographic principle. Physicists Gerard T. Hooft and Leonard Susskind proposed that all the information inside a region of space can be described by data encoded on its boundary. Later, Juan Maldacena's groundbreaking ADS/CFT correspondence provided a concrete realization, showing that a quantum field theory on a lower dimensional boundary could be equivalent to a gravitational theory in a higher dimensional space. In other words, gravity and quantum mechanics might already be two sides of the same coin. This holographic duality has become one of the most powerful tools in modern theoretical physics, linking black holes, entropy, and quantum information. It bridges quantum gravity with condensed matter systems, quantum entanglement, and even quantum computing. Testing quantum gravity directly remains one of humanity's greatest experimental challenges. The Planck scale is unimaginably small, far beyond the reach of today's particle accelerators. But physicists are finding clever ways to seek indirect clues. Gravitational wave observatories, like LIGO and Virgo, may reveal signatures of quantum space-time. Observations of black hole evaporation, Hawking radiation, or quantum decoherence in large-mass interferometers could provide the first empirical windows into this hidden domain. Meanwhile, astrophysical measurements of cosmic microwave background anisotropies may encode the quantum fingerprints of the early universe. Each approach to quantum gravity offers a unique piece of the puzzle. String theory unifies all forces through vibrational symmetry. Loop quantum gravity quantizes geometry itself. CDT builds spacetime from causally ordered simplices. Asymptotic safety ensures mathematical stability. And holography hints that the universe might be a projection, a quantum code unfolding from a deeper informational reality. Perhaps in the end, these ideas are not rivals, but fragments of a greater whole. A future framework may weave them together, revealing that the universe's deepest structure is both geometric and informational, both continuous and discrete. The quest for quantum gravity is more than a search for equations. It is a search for coherence, for a language that unites the stars and the atoms, the cosmos and the quanta. When we finally decode that language, we may find not just the architecture of space-time, but the very logic by which reality thinks itself into existence. If you found this content helpful, don't forget to like this video and subscribe to the channel. Leave me a comment. Let me know what you think about the different theories of quantum gravity. Join me next time for another deep dive into the strange and unusual world of quantum physics.